universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, and welcome all of you folks out there in KGRA land. How are you doing? And hey, look, it's Tara. Hey,
How you doing? Good to see you.
likewise. It's been a long time.
It has been.
Um, it is I, Mark D'Antonio, with Tara DeUlis, the other half of Sky Tour Radio, and also one of the founding members of Sky Tour Livestream. That's it, right there. See that? That that
And
that,
right there too.
that lady knows what she's doing. So, um, we're going to do a few things tonight. It's called Astronomical Potpourri. We're going to look at a few things that are interesting. We're going to talk about some of the developments in astronomy. We're going to talk about some of the really cool processes that we as astronomers use to determine the nature of the stars. Something that we really haven't gone into in this amount of depth before.
Cool.
We're also going to show the new app that SkyTour Livestream has, as written by our Bulgarian super fan and super contributor, Isabella. It's an app that actually contains every single observation in photos and data that we've ever done since 1919. No, since 2021.
Wow.
Okay, so it's several years of data all in one database, and it's searchable. You can find every time we say photograph the Orion Nebula. And what you can do with that is really interesting because, and in fact, she's done this too. You can look, and for those that don't know what Sky Tour Livestream is, I'll tell you in a minute. But you can look, for instance, at data throughout all the years that we've studied these particular objects and look for differences in the data. Now, you might think that something so far away like a nebula wouldn't change that much.
Right.
Not true. In fact, Isabella has discovered asteroids in our footage. Okay, she has discovered stars that have vanished.
Wow.
That's right, stars that have simply disappeared. And that's actually a puzzle because that leads to an idea that maybe there's another evolutionary path that stars can follow. We know that when there's stars like the sun, well, they'll become red giants and they shrink down to white dwarfs at the end of their lives. And so they end up as this white dwarf. Okay, that's one. Another one is we know that stars can sometimes explode because they're bigger in mass and they literally disrupt themselves. And that leaves a supernova in the center. I'm sorry, a supernova remnant, but it leaves in the center a neutron star. Okay, a star that's about the size of a city. All right. And that's a second way stars can go. The third way is that same process, but instead of a neutron star, it's a black hole. Yeah. Right. Black holes are really enigmas wrapped in a mystery. All right. And so trying to figure out what's going on inside a black hole is probably going to be the job of future civilizations beyond ours, because we can't get in there to see. We only have a theoretical idea what's going on. So of all those are the three ways and the three things we expect to see from what we call star death. Okay. However, there's another one where we see stars and the next few images, they're there, but then the image after that, they're no longer there. Now, if they turn into black holes, we would have detected a black hole. If it became a supernova and went into a black hole, we'd see the supernova remnant. If they expanded into a red giant and then made this planetary nebula and shrunk back down to a white dwarf, we would see all that. So we don't see a red giant. We don't see a white dwarf. We don't see a neutron star. We don't see a black hole. So what's going on? And where do those stars go?
We need to get our eyes checked.
and our J's and our K's.
Yes, exactly.
So the thing that's interesting is it's a new potential uh, mm, land.
Very
But
cool.
yeah,
How
new potential
interesting.
land for an evolution of stars. We don't really know what happens to the stars that seem to vanish. And you have to, of course, ask: are they vanishing because they weren't there in the first place? Are they vanishing because they were actually asteroids captured in the field, and then when it was photographed a year later, they're gone? Of course. Um, or are they some other type of transient object with a cosmic rays hitting the sensors straight on without making a splash mark like they usually do? All those are possible. But when you take away all of the possible items and you vet the data and you look it over, okay, Tara, when you look it over, at some point, what's left over, however crazy it sounds, must be at least on the way to the truth. So
Right.
it's
Right.
possible, yeah, it's possible then, right, that stars are vanishing in ways that we haven't heard of before.
Hmm.
The most likely explanation, I'll give you one, um, might be asteroids in the field that have simply orbited out of the way. But that doesn't explain seeing them there year after year after year, and then suddenly they're gone. Okay, you don't have an asteroid coming right at you, and then suddenly it goes this way. No, that doesn't happen. Or right, or away from you, and then suddenly it goes that way. Okay, so it would be either in the field or not in the field, or moving through the field over time as you watch the travel. That isn't what we
Okay.
see.
Huh.
So interesting. So it's not asteroids. Okay. Hmm. We know it's not a white dwarf because we can. The white dwarf is a visual spectacle. You could see the white dwarf, right? We have taken pictures of many objects that have white dwarfs in their center, and we can see them, and we can see like the dumbbell nebula. We can see the white dwarf in the middle. It's
Very cool.
thousands of, and maybe 1,500 to 2,000 light years away. We can still see the white dwarf, and the white dwarf is the size of the Earth from 2,000 light years away, and we
Wow.
can still see it. That's because it's very hot and very luminous because it's
Hmm.
very, very small, but very, very bright. Okay. So then the idea is, well, maybe stars somehow went down to just collapse into black holes. That's a strong possibility, but like when we looked at our black hole, okay, instead of this is actually the one in the Virgo cluster, the Virgo supercluster black hole. We looked at this
Wow.
particular one. We saw this one. Um, how do we detect it? Well, we're seeing it right here. We're seeing the detection. The detection was done using radio telescopes, and when radio telescopes turn up nothing in that region, then we know that they're not the black hole. Because all around this black hole, all that light you see, that gives off energy that you might see. The black hole, of course, takes some of that energy, all right, but you're
Right.
still going to have some type of radio energy coming at you. And that's something that we don't see either. So they're not black holes, they're not white dwarfs, then they're not asteroids moving through the field. Spock, what are they? Right? We don't know. We don't know. So this is a really cool branch of science that is something very interesting that we're looking at. And astrophysicist, someone I know named Beatriz Villarol, she's got a project that she's undertaking now to actually look for the causes of these missing stars.
Cool.
And it just so happens that Isabella in Bulgaria, our super fan, super contributor, is someone who has found missing stars in our own data from years ago. I mean, and so you can see where this is going. What I'm trying to get it out to everybody watching this, all one of you or two of you. Just kidding. Okay, there's three. I don't know. What I'm getting at is that there's going to be a resurgence of science that you can do, right? You can do, and you can use our data. You can use your own data. You can couple our data with other databases of data and see what's going on. Now, I've been mentioning SkyTour live stream, and whether all of you know it or not, I'll tell you. Basically, it's a clear night journey into the wonders of the deep sky, right? Now we have a remote observatory out in the Sonoran Desert, west of Phoenix by 75 or more miles. And Tara knows it well.
I do.
They've been out to that observatory. I've been out to that observatory many times. They've been out to it, I think, more than me. Okay. And on one of those episodes, when she was out there, they encountered something exceedingly, frightening. You remember that?
I think so. I'm
Yeah.
holding on.
Yeah. You know what it was, right?
Yeah, I do. It wasn't
What?
really frightening to me, but someone else was very frightened.
Oh, you want to tell that story?
Well, that's when I heard it's about the um the because I was out there with Marianne and we were working on the observatory
The
and
other part of the triumvirate for
she's
Skytrain.
Marianne's anyway, she was out there and all I could hear was and I turned around and she's pointing at the ground saying and Mark, why don't you show them what she saw?
I don't have. I was looking for the picture.
Oh, you don't have it? Okay.
I'm looking for it now. I have it. I
I
have it.
think
You ready?
Yep. I'm
This
ready.
is what they saw.
It was something so unexpected and
So cute.
it was right there under the computer where we were standing.
Oh,
and
that's a
sitting and
beautiful.
stuff.
That's a beautiful creature, the tarantula,
was.
the desert tarantula. And for most people that think desert tarantulas are just looking to bite you and kill you, they're not. These types aren't venomous.
Sweet.
They have long fangs, about that long, but you know what? To get them to bite you, you really got to work at it. They're actually very docile. In fact, they used to sell them in pet stores around here.
Yeah. Oh, they still do here.
Okay.
I see them. There's different varieties. Yes.
Yeah. They don't sell scorpions. Maybe they do as food. I don't know.
You can catch them. Just go out in the desert with your light. Catch them.
Yep. Yeah. So yeah, that was right. And so out in the desert where we have the telescope, okay, and
All sorts of animals.
that's me. That's originally when we first installed it, and we did some upgrades to it, and we actually ended up making this the final setup.
Nice. Well, the dew shield is that.
Yeah, the dew shield goes on the front of that, when it covers that red camera. It goes into the cylinder, which continues. Our camera's on the front of the telescope.
On the floor
there. Back.
Yeah,
there it is. It's in the back on the left. Right here. There it is.
Yeah,
right
that's it.
That's the dew shield right there. Yep. So
looks beautiful.
Yeah, this telescope, it takes advantage of these beautiful desert nights. We see things there, and when the sun sets, if it's cloudy, you have a beautiful night anyway because you see these absolutely stunning views. Okay, which I took this out there actually at the site of the Future Observatory. At the time, it wasn't there, and before the observatory was installed, I waited till just after sunset, and I took this picture. This is the summer Milky Way, and you still see the lights of sunset in this image down below. Now, there's a couple of lights over here that you see, but then there's lights of sunset along the whole horizon. And the Milky Way is still extremely visible. I mean, so that's quite dark out there. It's
you can see the horse.
That's right. Yeah.
Mm-hmm. I can see it from here. Yeah.
Mm-hmm. Yep.
Neat.
The dark nebula is something that is fascinating to me. The dark streaks you see in there, that's actually dark clouds of dust created by red giant stars on their outer atmospheres, liberated to the interstellar medium when stars go supernova. It's absolutely incredible,
Oh,
and
so
when we first made the platform for it, this was one of the first days. And that evening, after it hardened up enough, I set up a tripod on that, and I started taking pictures of the night sky for the first time. I thought it was really great. And then, of course, our own Tara made this door.
Hey.
STLS. That's the Skytrain live stream door. She actually made that door out of bottle caps. And the bottle caps were not changed in their color in any way. And I'm sorry for the bright white legs, which are causing people right now to blink really hard. I apologize for that.
Oh, my. Yeah. It's that Connecticut in you, Mark.
I know. And of course, and then here is our dear lady, Tara, staring at the telescope with the dew shield cover on top.
Saying, what the heck? How do we fix this?
Yeah, well, we've had our shares of bumps in the night with this telescope, but it's not bad. Not bad, but Now I run the telescope from here. I'm in Connecticut right now, and so I'm running it from here. This telescope you see right behind me, that's actually the East Coast telescope that I took out of the dome. We had an actual dome in the front lawn. That went over well in the town.
I bet your neighbors are sad that it's gone.
And
This
one
is
of them is
kind of a
actually because
landmark, you
it
know?
was a they would tell people who were coming over their house for the first time, look for the white dome on the front lawn. The next house is ours. you know. But yeah, I outgrew it. This telescope here, we're going to replace with a solar telescope so we can view the sun. Because the sun is actually a very, very, very interesting object. This is the sun here.
Cool.
Everything you see in that image is stuff that we're going to be able to show you. It's always changing. On the outer edge, you see those the fires sticking off the side. Those are called prominences. That's actually plasma, which is just the protons from atoms that have been liberated of their electrons, and so that plasma glows. And when those prominences on the edge are actually coming towards you, then they look like those black snaky lines that you see elsewhere on the sun. And those white areas, those are areas where there might be sunspots, and there are very, very hot areas around them, and so it'll glow a little bit brighter. You can actually see one sunspot right about there. If you look, just follow my finger, just left of center and just below, you'll see a sunspot, and it's surrounded by one of those bright areas. Those are called plages. And then down below, you'll see that large dark band that looks like a smudge.
Mm-hmm.
That's actually an arching prominence. And what it's doing is that's coming at us off the sun like this.
Wow.
Okay.
It's huge.
And as it leaves the sun from the side, it looks like this big arch, okay, with spindles and all these beautiful spikes going up to it.
Cool.
But from the top, as it's moving off the sun toward us, it's coming at us, but we can't really see it. But it's cooling off as it does so.
Mm-hmm.
And so that's why it looks darker than the background. All of those prominences are dark lines because that's material moving away from off the sun's surface.
Okay.
The surface of the sun is 10,000 Fahrenheit in temperature, and these are somewhat less. Okay.
Wow.
Yeah, probably a balmy 7,500 degrees Fahrenheit.
Oh, it looks like a curling iron burn scar and horsehair art, that squiggly line.
Oh, yes, that's right.
So, where they put horsehair into ceramics and bake it, and it squiggles just like that.
Interesting. See,
Mm-hmm.
take it from an artist who knows her stuff. I like that. No, it's a wonderful.
Mm-hmm.
That's a wonderful observation. You know. So yeah. So on the East Coast, we're going to have the solar observatory to look at the sun.
Very cool.
Ta-da! Like that.
Very
on the West Coast, we're going to continue to look at things like this, which are supernova remnants.
Ooh.
And we'll be exploring those all the time with our telescope out there. We're also going to be able to explore galaxies. Here we see a supernova and a galaxy marked by those lines, those red lines. We were able to capture that supernova in a distant galaxy. Very, very cool. You know, and that's the kind of thing that we like to do. Yeah. Remember, this is the stream where we caught a meteor striking the moon right at the middle of a lunar eclipse when the moon was the reddest. We saw this flash, and it was a meteor hitting the moon right at that point. That's a once in a lifetime.
Perfect time.
You don't see that more than once in your life, I think. You know, it's very rare. So every week, you know, if you want to join us, it'd be great if people would join us and they can actually, enjoy our stream. Not only that, but it'd be great if people could then, make an effort to support us in some way. We are a nonprofit organization. We're a 501c3. Thanks to her work along with Marianne to get that to happen. They were very, very diligent about that. And that allowed us to be able to get funding so that we don't have a whole lot, believe it or not. But we got enough to be able to get a second telescope for a second location. And we already have all the equipment we need, and we just have to actually do the installation. And that'll be in Benson, Arizona. Benson, Arizona, warm wind through my hair. You know, if
Don't
you
know
remember,
that one.
you
I
don't,
don't
huh?
remember that, huh? I'll have
You
to
got
learn
it.
it.
Yeah,
Okay.
it's from the movie. What was the movie? It's about the movie. It's a movie where these guys fly around in a spaceship and they have these intelligent bombs, and the intelligent bombs, they talk to them like people and they converse with them, and then the bomb goes off and destroys a planet. Okay, and
Dark
makes
Star?
Dark Star. That's the one. Exactly
Donald
right.
figured it out. Thanks, Donald.
Yeah, thank you, Donald. Was it Donald Cleanser? Yeah, Dark Star. That's
Oh,
right.
okay.
That is right. That's right. Yeah, and so Dark Star is a great movie, especially at the end when the bomb starts to have this existential crisis and decides he's not sure what to do, and he starts to get all religious. And at the end, he says, "Let there be light." No, you know, and it explodes.
The
Hilarious.
Dark Star is no longer dark, huh?
Yeah, yeah. Thank you,
So
Donald.
that's what's going on. That's how come the lights are turning on and off.
Yeah, yeah. Well, I wonder that, but we'd see the light. We'd see something happen. We'd see something.
In theory, yes.
Yeah, yeah.
Mhm.
It's nice to see that we have a lot of the Sky Tour regulars with us tonight.
Yeah.
Um, I want to say hello to Maria Wilson. Hello, Maria. And Jeremy B is with us as well. Hi, Jeremy. Nice to see you. And we have, of course, Genghis and Kathy, Daisy and Zoe are with us. And that Tara right there, she's with us. Yeah,
Hi.
Mark's not here. He's out there somewhere. A lot of
Aren't we
people
all?
joining us tonight. I just want to say hi. Craig Ansel here is with us, and this is an interesting question. Do you buy into the hypothesis that the matter entering into a black hole are released elsewhere, like a wormhole? Excellent question. The reason is I sat with Kip Thorne for about 3 hours. You may know him from the
Cool.
movie Interstellar. He was the consultant. I sat with Kip and we talked about black holes. He talked about white holes, and then he talked about an argument he had with Stephen Hawking about the existence of white holes. Because his argument was, if we could theorize white holes exist, and we don't yet, we can't see that yet, then theoretically, and he laid it out mathematically, and it worked. As you're entering the black hole for what would be your final trip, you could actually see your ship coming out of the white hole before you enter the black hole. So wait a minute, is that time travel in some way? And it's information time travel, yeah. And so it was kind of interesting to talk to him about that. So I don't know, Craig, whether white holes are real constructs. We know that the Einstein-Rosen bridge, wormholes, okay, by any other name, we know that wormholes are a possible construct that could exist, but we'd never be able to harness them for travel. And the reason for that is because think of them as tornadoes in space without the spin. They're conduits, okay? Like a tornado is a conduit between the upper atmosphere where the clouds are and the ground, and they're always moving. Wormholes would also be exactly, they would do the hula, okay, but not as regularly. They would kind of be all over the place, and they might evaporate for a bit of time and then come back.
Wow.
They're not a reliable source, and the amounts of power, excuse me, required to have a stable wormhole is something that we can't possibly conceive of, nor do we know how to use vast amounts of power to make a stable wormhole. So if it's astronomy, a conundrum that we can't solve, that's okay. At some point, maybe we'll figure that out. Maybe we'll figure out some ideas. I don't know. I just think it's, I just think it's a little bit on the fringe right now. We can't really say whether it's real or not. But that's a great question, Craig. If you got any more, please drop them in. This is we're going to do astronomical potpourri. I've got a few things to do as well here, and Tara's got all kinds of questions. You can see. Look at her right now. She's got one. She's about to ask one.
Well, I just was thinking about that. So didn't it used to be that that was what the theory was the wormhole? theory, and now it's more, is it, if I'm going to say it, or the Albuquerque Drive, if I'm saying that.
Alcubierre Drive, yeah.
So is it just kind of shifting now that we know we'll never have enough power for wormholes, or is it? To me, it seems like that's how they're always talking about the tortilla and bending space and going through.
Yeah.
You never hear about the wormholes disintegrating or losing power or shifting around. It's always a straight shot.
Yeah. The wormhole concept and the Alcubierre Drive are two different concepts.
Right.
Different mechanisms, different mental process, different thought problems. And the Alcubierre Drive is a warp drive. It warps the local fabric of space. A wormhole connects two different spots in space with a conduit. It doesn't warp space per se. Okay, not on the outside. The Alcubierre Drive, when you're in the ship, you're warping space around you. You're folding the space so the distant destinations come closer to you. All right. And the destination or the origin where you left from gets further away from you. So you're shifting that, So you're doing this. You're actually shifting. You're shifting the distance. The way that works is you're basically making a trough in front of you of warp, bringing the distant object toward you and lengthening what's behind you. So you can make these jumps with the Alcubierre Drive and move your way to distant locations much, much faster. However, you're moving from point A to point B. You're actually traversing the space in between point A and point B. You're not sidestepping any of that. You are indeed having to travel that distance. Therefore, if there is an errant asteroid anywhere between you and your destination and you hit it, you're dead. So that's when that was one of the problems. And never mind the energy required to make what's called the warp bubble that allows this all to happen. That's let's say we can do it. All right. It's colossally improbable that we can, but let's say we could do it. If you wanted to travel safely from here to, say, Alpha Centauri, then you need to shunt away any debris that's in your path. Okay. And to do that, enter a physicist named Froning. That's the last name. Okay. And Froning came up with a variation of the Alcubierre Drive. So it's called the Froning Alcubierre Drive. And that's kind of like a starship in Star Trek that has its shields up. It pushes stuff away. All right. And it also bleeds off energy that builds up on your windshield, like bugs on your windshield, because that's going to happen with the Alcubierre Drive. It's not particles that build up on your windshield. It's energy. And when you stop, all that energy goes, wow. So you might get to your star system you're investigating and see, just as you're slowing down, all these planets, all these starships. Holy cow, it's a burgeoning life forms here. And then when you stop, all that stuff goes,
oh no,
and blows it all up.
Oh no.
And then you go, oh. And you look at your friend and say, let's just say we didn't see. Yeah, you're right. Let's just say we didn't say anything. Yeah, we didn't say anything. Let's just step out of here really slowly. Yeah. So the Froning Drive, or Froning Alcubierre variant, would actually bleed off all that energy as you're going, and also shunt particles around you that might be damaging to you as you're making the trip through that warp space. So that's pretty cool. All right. So you could go from here to Alpha Centauri in 7 to 10 days. Now, that sounds like a long time if you're driving in a car. It sounds a very long time if you're flying in an airplane. However, if you're going in a spaceship through the universe, where Alpha Centauri is actually a 10 to a 12,000 year trip at the fastest speed we can currently go, that sounds like a dream. Okay. However, it's actually too slow. You can't investigate and explore the universe moving only at that rate of speed. You need something else. And that'll be for a future talk, but it's one that I do around the country. And it has to do with interdimensional travel. And that's something that maybe we'll talk about next week. And I'll go through that. I actually did the talk on Sky Tour Radio. You can find it in the archives. It's a few shows back. And you were with me on this. And we talked about the interdimensional travel. So you can enjoy that and find it all there. All right. Let me see now. And I do want to
Thank you, Mindfork. Did you see that
the,
for
the
his
witch and
donation?
the witch and Bugs Bunny had one as a pet. Well, his name was
The little
Paul.
kitty. Was that it?
His name was Paul.
Oh, that's a funny name.
I try to remember. Yeah, Chris Mindfork. What did she say?
There we go.
Oh, look at that! Thank you so much, Chris. That was very kind. Very, very nice of you. Thank
Yes.
you so much. Wow. Yeah, and yes, interdimensional travel is probably how they're doing it. Kind of interesting because Avi Loeb at
Hmm.
Harvard, and many of you know I worked with Avi on a couple of television productions, independently, but we know of each other. We've talked to each other. Um, he just came out with a statement that he thinks that maybe aliens are traveling interdimensionally as well.
Hmm.
So that's kind of
Really?
interesting. I'm pretty, uh, I'm pretty excited about the fact that it's catching on out there. And there's a lot of people in science that are joining us in this chair. You know what I mean?
I just can't wait till they figure out how it's done because I'm
Yeah,
interested. I'm
yeah,
interested in it. And
yeah. Think about it this way though: if we could do the interdimensional travel thing, and I will be honest with you, this is not an exaggeration. Okay, if we could do interdimensional travel, it means that we could go from here to Pluto in about maybe 15 minutes, maybe 10 minutes, have lunch in orbit around Charon, its largest moon, and then come back here, you know,
okay.
and be back like, an hour later. So in other words, um, the interdimensional travel option, of course, it would be an expensive trip because we have to, use our particle accelerator, which is what I think is in these ships to generate these particular particles that take us there. Okay. Thank you, Cindy Murphy. Cindy Murphy, such a sweetheart. She
Thank you, Cindy.
did a nice
Awesome.
super sticker for us. Thank you. And but these particles would drag us into an interdimensional space that would allow us to travel through a warped universe very briefly, and thus, when we come out, 1 foot here in our four dimensions might translate to, 1,000 feet if we travel a little bit into this warped dimension. But if we go far enough into this warped dimension, uh, you know, 1 foot or 100 feet in there in regular space might translate to the distance to Pluto. Okay, so that's it's a highly warped dimension outside of our own. I know it's crazy, isn't it?
It's fascinating, but this is all theory, correct? Because I mean, we don't. I mean,
Yeah, the thing that we need to the thing that we need to be able to understand is the fact that we have to show that string theory is real. Now, oh, thank you, Kathy.
thank you, Kathy. That's
Yeah,
awesome.
see,
Thank you.
we have the best people in Sky Tour. Everything we do, Sky Tour Radio, Sky Tour
Mhm.
live stream. They're just
Generous
phenomenal
people.
people.
Thank
Yeah,
you.
they are. They are.
Hmm.
You know. When did you talk about Hansel and Gretel, by the way?
Oh, up at the top because one of our guests, Renee, was going to the animal shelter to pick up a cat, and so and there she's being sweet about it. I just rescued two little kittens from the Phoenix heat, and they're called Hansel and Gretel, and
Oh,
they're just little babies. So
there.
cute.
I gotta say,
So
she sent me
cute.
the photos. They are absolutely little cutie pies.
They're like
I
eight
gotta
ounces.
say, I love 8 ounces.
8 ounces was one.
Oh wow,
Gretel and Hansel's now 1 pound 2 ounces. They're different litters, so
wow.
they're cute.
I have to say, the funniest videos that I watch are cat videos on YouTube. I'm sorry. Okay, I like watching cats do stupid things. Go figure. Okay, I'm sorry, but I like watching cats try to jump to the ceiling fan while it's moving, and they go.
Oh, they're just so silly and just free with their silliness. It's a really good therapy for anybody.
I think you're right. I love, for instance, like a cat standing on the edge of the couch, and you can see it going through its head. I'm going to jump to the counter 3 feet away, and he goes to jump, and he goes, eh! he literally goes less than the length of his body and falls. Oh my gosh, that's hilarious.
So
Yeah.
that gravity in this universe is strong,
Yeah.
no matter what you are.
The force is strong in this one,
Mhm.
but not that one. Yeah.
So sorry
So
to
yeah.
distract, but that was great.
No. I think that's fine. I mean, that's just fine. So the bottom line is, we're actually moving along with Sky Tour live stream, right? We've got the existing telescope out in the Sonoran Desert, which I showed you photographs of. We have another one going into Benson, Arizona. We have everything we need for that. Currently,
Yay.
that's set up in Marianne's office, which is our Sky Tour main headquarters. And it's I can run it. If it was plugged in, I would do it now just to show you, but never mind. Okay. And then here in the East Coast, I've got the telescope we're going to put in out here that's going to give us solar imagery and show us the sun the way you saw it here. Okay. So we're going to have 3 observatories. And then I'm looking forward to working on our mobile observatory that we can take around the country. Okay.
Yes.
And on the outside of that, we're looking for a Southern Hemisphere observatory location right now.
Wow.
So we can put a telescope down in Australia.
Okay.
Well, that's precisely because I like to talk like this. For
Oh,
18
God.
years I've been doing this. So, hey, I think it's okay, So I can't wait to go there. I can't wait to, fly 23 hours on a plane.
Yeah.
Yeah, it ain't going to happen now. I can tell
It'll
you
go
that.
so quickly if you ever do that, because you know what you're going to do when you get there is you're going to play with your telescopes and get it set up and live stream.
Yeah, the trip back is going to be, I can't wait to get home so I can use it now. Yeah. But anyway, so that's all cool. But so I did want to cover some actual astronomy tonight, and I'm going to do that.
Cool.
Obviously. One of the things I want to talk about was what's coming up very soon here, and that is the Perseid meteor shower. Raise your hands if you know about the Perseid meteor shower. Okay. Everybody in the chat will probably raise their hands. The Perseids are a remnant of a comet, okay, and that comet was called Swift-Tuttle, and it orbits the sun every 133 years. And in that debris that it leaves behind, I'll tell you exactly what that debris is in a moment. Sometimes the Earth flies through that stream of debris, okay, and when it does, we will see meteors coming into our atmosphere. And that's the meteor shower. Most meteor showers come from comet tails that we're flying through. So what are comets? Comets are actually icy balls, I guess you could call them, icy bodies from the outer solar system, from our outer halo. We have the planets in the inside, about that, say that the Earth to Pluto, or Sun to Pluto is this big. Okay,
Wow.
let me make it smaller. Say Sun to Pluto is this big. We have an outer halo that's huge. It actually stretches possibly almost 2 light years away from our sun. But when stars pass by in that outer area over millions of years, the little gravitational perturbations of other stars passing near that cloud called the Oort cloud will perturb some bodies that might then fall inward and reach the inner solar system some millions of years later. And when that happens, they might fly and circle the sun. And when they circle the sun, they'll come in, the gravity pulls them in, and they fly back out. And maybe they'll make elliptical paths, and they become periodic comets, okay, where they come back every so often, the same way Halley's Comet, every 86 years, okay, things like that. So, but the icy debris that they leave behind comes from and gritty dirt. In fact, regolith, the material that they're made of, comes from the many impacts by asteroids in the solar system hitting each other. There's myriad of dust particles out there, and they get attracted to small bodies. They get attracted to asteroids and planets. Okay. And so this material falls onto the comet body, right? But
Mhm.
because the comet body is also very, very cold in that deep dark of space, where the sunlight doesn't hit it, um, the impact causes a tiny, tiny bit of friction, and that tiny, tiny bit of friction will melt any ice that's surrounding these particles and cement them together.
Mm.
Multiply that by trillions, and you've got a cometary body. Maybe the core is an old, like a rocky asteroid, potentially an asteroid a few like a kilometer across, or maybe a few hundred meters across, maybe a few meters across, and then the rest of it is all this icy material. Now we think of ice, we think of water.
Right.
Yes, we have water. We have carbon dioxide ice too, ammonia ice as well. We have
Mm.
carbon compounds that are in these comets, and these are the original population of our solar system. These are the oldest objects in our solar system. They were made with the solar system. So, being that the comets are here and have been here, this is something uh, that we can always look at and say, hey, if we can study comets, we're literally studying the ancient solar system by studying the
Mm.
freezer that is that these are now kept in. And they're just a
Interesting.
snapshot in time, right?
Yeah, it's like an ice core, I guess, you know?
That's exactly right. A very good,
Mhm.
very, very good example. An
Yeah.
ice core is a snapshot of history for our atmosphere, and if you can get ice air bubbles out of the ice core, you can sample what the air was like and what it was made of back then. That's something that they've done, right? So it makes sense then that studying comets is really important. Now we get many different types of compounds on a comet. We get um, carbon molecules. We get carbon molecules. We get carbon compounds of all kinds. Hydrocarbons. Some a little bit more complex than others. Hydrocarbons, of course, are part of the building block soup of life. We get ammonia ice, NH3. We get methane ice, CH4. Okay. We get all kinds of um, these primordial ingredients to life out there, and they're frozen forever on the surface of a
Mm.
comet until it reaches the inner solar system. When it comes in and it goes around the sun's radiation begins to melt that ice. And when it melts the ice goes from being this solid substance to H2O molecules, vapor. So it
Mm.
goes immediately, it doesn't reach a liquid state. The pressure is too low. It just goes right to vapor. And as it does that, there's a force of the impact of that solar radiation on the comet. And when it melts that ice, there is sometimes trapped gases inside the comet, which cause jets of material to shoot out. And so that jets of material shoot out different other ices, but it also shoots out stuff like regolith, dust, and dirt. And that stuff ends up being left behind the comet's orbit. As the comet orbits the sun, it leaves behind this garbage path of debris. It's like Pigpen in the Charlie Brown
It's
comics.
the tail, right? I mean, that's what you're
That's right.
talking about. Yeah.
That's called a dust tail. And it's like Pigpen from Charlie Brown. Wherever he walks, you see this cloud of dirt behind him. That's a comet. Okay, comets are the pig pens of
Uh-huh.
the solar system.
How funny.
Yeah, yeah, and so that dust is what we fly through, and that creates these meteor showers. And one particular comet, Swift Tuttle, who has, as I said, a period of meaning time it goes around the sun, 133 years, uh, that left a trail, and the Earth's about to fly through the trail of the tail of debris from that comet. And if we're lucky, we could see anywhere up to 100 an hour, 60 to 100 an
Wow.
hour. Yeah,
So do
yeah.
they try to capture remnants of that tail? Is that impossible to do, to look at a
Um,
comet? How do we look at those comets when they're so close to us?
well, we would see those that being that's just debris, we'd have to collect it out in space, and
Mhm.
we've done that. There's been a mission to collect material, interstellar dust grains that would be from comets out in our solar system,
Oh.
and we returned some of that. I recall this one mission, the parachute never deployed, and
Uh-oh.
the thing crashed. but it went edge on into the desert, thunk, and they actually could retrieve something from it. There was enough left intact, sealed in, that they could actually retrieve some interstellar dust grains, which is kind of
Cool.
cool. Yeah.
Cool.
so then these meteor showers come from a parent comet. Okay. Now, as far as the timing, every year the Perseids occur here on the Earth, and that they occur between August 11th and August 13th. And the peak time to view is, if you can get away from city lights, the peak time to view is going to be around midnight or after. All right, midnight till dawn is the best time. And there's people going, "Oh man, I'm not getting up at midnight." Well, then you'll miss the Perseids. Okay, so I think that that you would have a great time looking at them. It's actually kind of a family event. You keep the kids up late, go on out and say, "We're gonna watch for meteors," and you lay a blanket out, you look up in the
Yeah.
sky, and just watch.
And
You
it's
know,
fun. It's fun.
it is a lot of fun.
Mhm.
Now, the thing about the Perseids is the Perseids are actually a rather special meteor shower because they're known for how bright they are,
Ooh,
and
cool.
they're known for how fast they leave long trails behind them. All right, of light and color. And sometimes you'll actually see a trail of what looks like smoke, and that's exactly what it is. Now they're going to be 90 miles up, okay, in the atmosphere when they're coming into the Earth's atmosphere, but they're coming in at tens of thousands of miles an hour.
Huh.
Okay, so, and now here's the question I'll pose to folks: how big is the average meteor in size before it burns up?
Mm.
How big is that piece of dust or dirt or whatever that's coming into our atmosphere? Is it
This
a
this sounds like a trick question to me. But
trick question?
isn't it a lot smaller than we think? With the brightness, and I'm curious when you said that leaves a long trail. I mean, would it have to have more material to leave that, or is it burning something different?
Well, I mean,
Football size, that's a good one.
yeah, Carl
Mhm,
Becker says football size.
mhm.
If anybody else has a guess, please throw it in there.
I say a
Um,
fist size.
okay, fist size from Tara.
Mhm.
Okay,
Hmm.
right. And keep in mind that they're moving very fast. Um, and I think that you'd be surprised to know. And Chris Mindfork says car size. Actually, I give you a little hint here. A car-sized meteor is what struck Chelyabinsk, Russia,
Oh,
and the shock wave from that explosion, 90 miles up in the atmosphere, blew out metal security doors, bent them in half, and hurt several thousand people.
flattened the
Okay,
forest, right?
that was Tunguska.
Oh, okay.
Okay, and that might have been a small comet. Okay, Sam S
Hmm.
says a dime. Three Beards, a great guy. Three Beards says basketball.
Yeah,
Okay,
great guesses.
so yeah, these are all good guesses. Yeah, but like we said before, the car, that's too big. Um, the closest person so far, and we'll just go for the answer here because we're gonna be heading to a break shortly. The closest person was Sam, and when he said a dime, but in fact he was quite far off even from that. Okay, because uh, a dime sized uh, meteor striking the atmosphere would make one of these meteors that would be so bright as it's crossing that no one would miss it, and you'd see it during the
Oh,
daytime.
wow.
Okay, now the size of the typical meteor that people see in the sky is literally the size of a grain of sand. Go to the beach, sift out a grain of sand, a singular grain of sand, and that's what the size of a typical meteor is, plus or minus. Okay.
Um,
Yep.
how can something so small emit so much energy?
What a question. Now, see, that's a beautiful question. I did not set that question up with her guys, but it's
Hmm.
like the logical next question to ask. And here's how that works. Um, when something is entering the atmosphere at thousands of miles an hour, it crosses through space, then it hits an atmosphere. It's starting to hit atoms of atmosphere. When those atoms of atmosphere strike this particle, what's happening to that particle? It's heating up.
Warm. Yes.
Friction is heating it up. So if we slow it down, like let's make it slow. Okay, if we slow it down, you'll see that thing glowing red hot in no time, right? But it won't be melting and reaching a point where it's going to explode into, as meteors often do, until it reaches a certain temperature and pressure. When it reaches a certain temperature, now the atmosphere is trying to slow it down, and it's taking what's called a massive amount of kinetic energy, the energy associated with fast moving objects, and it's trying to convert it to heat. And it's slowing it down drastically as it reaches the Earth's atmosphere from thousands of miles an hour, tens of thousands. And so when that happens, it happens very, very quickly. It reaches the maximum possible stress point that it can handle. And when the meteor crosses that threshold, it literally disintegrates and all of it just burns up in an instant. That's why when you see meteors coming, you see a streak and then a flash and then a little streak as it fades out. They're all like this, like a streak, flash, and then it fades for a bit. That's because you're getting this meteor coming in, starting to burn. Oh no, it can't handle anymore. Flash, it all burns up, and then the little pieces just fade out. Yeah.
Or
So,
meteorites fall to the ground, perhaps.
yeah, the bigger they are, they can.
Mhm.
As a matter of fact, E-Man says something very interesting. How painful would it be if you got hit by a meteor? We can ask someone because just a
Oh
few
my
miles from here
God.
in Weathersfield, Connecticut, a woman was sitting on her couch in her living room when she was struck by a meteor.
Oh my gosh.
That's right.
Hello.
Yeah, the meteor actually went crashed through the roof of the house, went into the basement, bounced off the floor
Oh
of
my
the
God.
basement, came up through the living room floor and smashed into her thigh.
Oh
And
my
it made a
gosh.
black and blue mark, literally, this big on her leg. So I
Big
would say if they had lotto back then, she should have bought a lotto ticket.
one. Well, you hear
Yeah,
some strange stories like that, just these random freak accidents and right place at the wrong time.
that's right. He was on the right place at the wrong time. Exactly so.
Yeah.
So when you look for the Persians, they're going to be very bright, and you're going to really see this really bright streak. And they tend to be yellow. There's a lot of iron in them typically,
Mm.
so they're going to be yellow. You're going to see little yellow iron. Now, the interesting thing about this particular meteor shower, and there is some significance to it actually, and that is that when we look at the Perseid shower, the first time it was seen was 2,000 years ago,
Mm.
right? Chinese astronomers saw it back in 36 AD.
Wow.
Yeah, and um, the culturally, they've been called the Tears of Saint Lawrence in
Mm.
Christian traditions because they occur around the feast days of Saint Lawrence, which is on August 10th. So that's kind of cool how astronomical events influence culture, but they always have and they always do, as you know.
Yeah.
Eclipses were considered the dragon eating the sun, and you go bang pots and pans. And the oracles always said, "We're going to be all right. I'll make sure the sun becomes clean again." And he was always right.
Oh, thank goodness. Thank
Yes.
goodness.
Yes. Yeah, if it wasn't for eclipses, oracles might not have had such a colorful career, you know? So, as far as observational things, one of the things about these is uh, that when you study meteor showers like the Perseids, they help us understand the composition of comets. To your question before,
Mhm.
okay, and the behavior of these small celestial bodies like comets in our solar system. That's actually something that studying the meteors can actually do for us. And not only
Cool.
that, of course, they're just an amazing photographic opportunity. It provides opportunities for astrophotography to capture these gorgeous things. Our all sky camera out in the desert, now that I've upgraded it and built this new camera, it shows the beautiful sky. We're going to see the Perseid meteors at night, and it's going to be really
Cool.
stunning. Yeah.
Very
If it's clear.
cool.
It's usually
Yeah.
clear out there, but lately with the monsoons, it's kind of hard.
Mhm.
Monsoon's coming to an end, though, I believe, right?
Well, now that it's on a calendar schedule, I just don't pay attention much. When I was growing up, it was just when the moisture got here. So
Yeah.
it doesn't feel real moist out right now. It's really dry.
Okay.
Hot. Very hot. So.
We'll see. Marianne said today that it's actually quite humid out. And I have to laugh. Humid.
2%, 3%.
Yeah. To her,
No,
humid
it's
is
more
like
than that.
15%.
Yeah, it is humid when you're in Phoenix.
We live in 64% humidity every day minimum. And that's a dry day.
And you have bugs too.
Yeah, if you know nothing else, right? Well, you don't have, though, that we had here. End of July was the firefly season.
Oh, how
and we
pretty.
had all these beautiful blinkers in the night sky.
Oh
yeah, it was really pretty.
Yeah.
You look in the trees, and there's like tons of yellow lights going off in the trees. Yeah.
Oh, that's awesome.
Fireflies are stunning.
Did you used to catch them as a kid and think they were stars?
Let
them loose in your room, so they're all.
We used to catch them by the hundreds and put them in a jar, and we'd hang the jar in our tent. And those were our night light. If we wanted light, we just tap the jar, and they're all.
Oh, funny.
We'd have light for about 10 minutes until they calmed down.
Awesome.
Isn't that crazy?
That's really cool.
Yeah. Well, it's about that time. I think we're going to be heading to a break here in a moment.
Mm-hmm.
When we come back, we're going to talk about star colors and all the things that star colors mean and what it tells us.
Okay.
All right. So I hope you guys will stick with us. This is Mark and Tara for Sky Tour Radio, and we'll be right back. Ta-da!
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you would like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected. Only at kgradb.com.
Bum. Oh, hi. Yeah, I just wanted to. I'll come back to that in a minute. I just wanted to share that that there was one of the ad sets there. That was for our Etsy store for Skytour Livestream. Again, we're a nonprofit organization. We're not making money at this. Okay, but Tara said, "Yes, I know." But
Not what it's about for us. But
it's not what it's about. It's about the passion of getting the word out there in astronomy. So if you want to join our Patreon or become, a subscription member, you can go to our skytourlive.org page, and skytourlive.org is wonderful. Skytour Live portal right there, skytourlive.com, skytourlive.org. And if you want to email us, you can email us at contactskytour@gmail.com. All right. But do join our Patreon, okay? Because we have a subscription for everybody. We have a few members now. We'd like to have more. And I also want to take a moment to put out a little bit of feel for UAPPD. UAPPD.com is Marianne's special organization she started. And she and Dave Rich do UAP phenomena as seen by police forces around the world. And she's got, 50 or 60 stories now from different police forces and climbing, so it's kind of cool. I thought I'd throw that little shout out to her because she's not here. And therefore,
very cool.
When she hears it, she'll probably say, "He did what?" Now, before we go into the colors of the stars, I wanted to show you some of the colors of the stars. And to do that, I told you that we have an app. The app is, I'm in the process of setting it up to go live on iPhones, Android, PC. I'm going to use the PC version of our app right now, and it'll be on the Mac too. But this is it. It's right here. All right. And this app is interesting because let me just do it this way. There we go. This app is interesting because when we look at, okay, I don't want that either. I want, it's better. Okay. This is a compendium of every observation we've done over the years. All right. And it is a beautiful rendering that Isabella in Bulgaria put together for us. You can see a gallery of objects that we've captured, and we'll go into what that means in just a minute. There's Mr. Mooney. Okay. And this goes on for pages and pages because, as an example, this latest observation from the 2nd of August, which was the last stream we did, which was 2 days ago, it represents observation 1799.
Wow.
So we're approaching 1800 observations since year 2021. And so we can look at it this way. And if you click on the object, like I'm clicking on that one, it brings up another page. And this page shows you all the data associated with the image we took. Tells you the designation. This is the Eagle Nebula, measure 16, NGC 6611, otherwise known as the Pillars of Creation. You might remember that famous photo taken by the Hubble Space Telescope, right? And now by the James Webb. And this was on the 2nd of August of this year at 9:35 and 46 seconds. So, and tells you where it is. And so it gives you all this stuff. You can download an astronomical data file. You can download a PNG file, which is the actual full-size file. You can download just a folder. You can see the object folder. You can see the actual live stream when it took place. But if you click on the image itself, you can actually get in and look around. There are the pillars of creation right there.
Beautiful. Wow. It is.
It's beautiful. Yeah.
Oh, great.
And we actually we did this image in, well, if you don't remember how long it took to get this image, we look down here and we see it was a 25-second exposure right there. Yeah. And we had the gain, that is a sensitivity of the sensor, set at 200. And we did 15 such images like that. And by stacking them together, we get images that have less noise in them. They look much better. All right. Another one we did was this one. This is the Omega Nebula. Okay. This was another 20 exposures, and we did 29 of them. All right. And so when you look at this one, you can see beautiful blue, this blue, subtle blue in here, along with this red. The red in these nebulae is ionized hydrogen. It glows red. Okay. Just like around me right now. I'm an ionized hydrogen cloud. Okay. The blue is dust that is actually scattering the starlight. And those are called reflection nebulae. All right. So, and remember, the universe is in 3D. So when you look at an image like this, here's the thing to remember. When we look at this image, we see this part of the nebula, we see this part of the nebula, and then we see this darkness between. What that actually is actually dark dust that's between us and the nebula behind it. Okay, so you're seeing dust here, and the nebula is behind it, and so it's cutting off part of the nebula. So this is cutting off the rest of the nebula here. So this nebula goes behind the dark cloud all the way to here, but it's being cut off by this large, sinuous, dark nebula that's cutting through here. There's more up here. See what's happening there? And Tara knows. We've talked about this, but this is how that works. So it's really kind of cool.
Yeah, it is. It's counterintuitive of what you think, though. You think that there's windows that you can see behind.
Yeah.
The dust in front. So
yeah. And people for years thought that this was another new nebula off to the side of it, and then they realized, no, this is something that's obscuring what's behind it.
Wow.
Yeah.
Beautiful.
And by going through our data like this, you can actually see this and get a great idea of what's going on. Now, if you like that way of showing the data, that's wonderful. Our nice table here, or our gallery. Okay. But another way you can do it is you can get a straightforward table and go through that way if you want to see it. Okay. Not nearly as exciting, but then if you want to just look for different objects, you can go to this next tab right here. And these are the object tabs. EN means emission nebula. RN is reflection nebula. DN is dark nebula. Yeah. VN is variable nebula. SNR is supernova remnant. PN is planetary nebula. And then we have open clusters, globular clusters, star cloud. Okay. And we have just a star. We have galaxies. This is the Andromeda galaxy that we took. We have molecular clouds, which are also, see, the designations can be, it's an emission nebula emitting this red hydrogen. It could also be a reflection nebula emitting a bluish light, and it can also be part of a large molecular cloud.
Wow.
So in our database, it'll say emission nebula, EN, molecular cloud, MC, and reflection nebula, RN. It'll have all that in there, you know.
Look at those.
Yeah. And we have, of course, lunar eclipse, right? Moon. So now we can say when we click it, it describes what's going on. Then you can say, show all images of the moon. And you click it, and now you can see all the images of the moon in one shot through all the ones we've taken for years, over the years. Isn't that pretty?
It's amazing.
Yeah. So that's really cool about this app. And that's, again, Isabella in Bulgaria took it upon herself to do this with my blessing, and she's done a phenomenal job. Now, if you're done with looking at object types, then you can do this. Well, what did you look at in August? Oh, well, here we go. Here's August. And on August, what was this? This is July 30th. We looked at Bod's Window, the Chinese Dragon Mosaic, Lagoon Nebula, etc. And then we looked at On the second, we looked at the Butterfly Cluster, Ptolemy's Cluster, Omega Nebula, and Eagle Nebula. So you can see what we did. And if you go back a month, you can see these are all the streams we did last month. You can pick on any one of these and actually go. Like we had a Comet Olbers. And when we look at Comet Olbers, you just clicking, and this is what we got. The comets right there. Yeah. Really pretty.
Mm-hmm.
Yep. So we had all kinds of stuff there. So really neat stuff. And so you can basically, you get a sort of a guided tour of the cosmos with us here. And I think that this is something that people might like. Now, as far as a histogram, well, this is a weird one, but it shows you which objects we photographed the most. And if we go to this guy, it shows that we photographed the Rosette Nebula very many times. Okay. And so if we we can go to the gallery and look at the Rosette Nebula, but we can also search for it up here. We can just say Rosette Nebula. Right? And there it is.
So pretty.
Yeah. So this application then is something that is really a go-to for a lot of people. Now, keep this in mind. You could download all these images and compare them and see what's missing or what's new in some of these images. Did this tendril of nebula look different back in 2021 versus 2024? Okay. This is March 2nd, 2024. Let's go back down to the bottom here. And this was 11/10/2021. So here's what it looked like in 2021. Is it the same or is it different now? You know, did something change? Are any of these stars in different places? Turns out that Isabella, using this app, has found, in fact, that stars have moved from one place to another. Not just vanished, but moved as well. Because stars do move. They aren't immutable. They don't just stay there. Every star you see in every picture we've ever taken is moving.
And so are we.
And so are we. And sometimes we're moving with them, against them, in every direction around them. All of us, though, are orbiting the galaxy. We've orbited our galaxy about 20 times over the last 4.6 billion years. It takes about 230 million years to go around the galaxy once. Wow. So it's really something. And so that said, now the question is, well, where is the center of our galaxy? Well, the center of our galaxy is actually right about here. Okay, this is called Bod's window, Baades, Bod's window, and it is looking toward the center of our galaxy. I know this looks like we're looking at a wet driveway, guys. Okay, but it's not. This is all stars, stars beyond stars. And you can see some faint globular clusters in here. Okay. And you can also see that there's some dark nebula in here, streaks of dark nebula. And Bod's window is actually the only identified hole that allows us to look through almost to the center of our galaxy. Because there's a lot of stuff, a lot of dust blocking the center. Bod's window allows us to see as far as we can toward the center of our galaxy, which is kind of cool. Yeah, that brings new meaning to the term. You can't see the forest because of the trees.
And isn't there a black hole right there?
It's right. There's a supermassive black hole called Sagittarius A.
You'd never know it.
That's right. Yeah, not from here. No, you can't. So this is kind of interesting. And we also do these things here. We actually create these are called astrometric images. We actually identify, and all you do is click a button in there and you get identifiers showing you what's what in these different places that we go to. Right. And so this is because the telescope knows exactly where it is. And it identifies things on the screen and immediately puts the identification out there for you. So we do that for almost every image now. We actually show this very thing. You know, here's another one. This is called Ptolemy's cluster, and this one, again, you can see this beautiful dark nebula down here, right? And then you see Ptolemy's cluster. And this is a cluster of stars heading, again, toward the center of the Milky Way. And if you wanted to know what they were, well, we have that too.
Okay. There we go.
Here is the identifier.
That's really
Ptolemy's-
handy. Not
Yeah, Ptolemy's cluster is Messier 7, all right?
Hmm.
And it identifies stars, it identifies clusters. And if it's like, well, what is that thing in there? Well, this will help identify it, okay? So pretty cool. It doesn't know everything, but boy, it sure knows a lot.
Do they name the dark nebula?
Yeah, dark nebulae are very well known. So they name them. And they give the names among the names they give. There's several. Lind's Dark Nebula catalog has a bunch of them. Barnard's catalog is the most famous. E. Barnard was an astronomer who studied dark nebula exclusively. If I lived back then, that's what I would be doing, because I believe that dark nebulae are the clues. And actually, as I have often said, life begins in the dark. So I even wrote a song about that. Life begins in the dark. And it's actually something that we should really understand, because it's within these dark nebulae that life begins. In these dark nebulae, they have molecules. They're cold, and this cold, dark areas is where hydrocarbons can be made, and where carbon compounds can make bigger carbon compounds and go into these larger molecules that we're used to seeing here on the planet. Also in there is where clouds condense by their own gravitational forces because of their compactness. And we find that these clouds will condense down enough so that the hydrogen at the center possibly can be made hot enough to form a star. And then maybe planets can form around those stars that are formed. Okay, these clusters we've been looking at were all formed in such a dark nebula, and then they started illuminating the nebula they were in and causing that gas to glow, and then they became a stellar nursery or an emission nebula, the EN designation we talk about. They went from being a DN, dark nebula, to an EN.
Very cool.
Yeah. This is a satellite trail going through the image. You can see very faintly. Yeah. So this is an example. Again, this is the butterfly cluster, it's called. These are the antennae of the butterfly right here.
Oh, cool.
There's the head, the body, and the wings. Okay, see one wing, two wings, one wing, two wings. Apparently he's being shot down by an anti-aircraft gun because there's the blast. I don't know. I'm kidding with that, of course. But again, this is our nice astrometric identifier, and you can see this star right here is called Hipparchus 86527. Now, if we look this star up, Hipparchus is a star catalog. We look that up, we can find out why it's red. We can find out what spectral type it is, and that'll tell us, is it a red giant or is it one of these M-class dwarfs, these really tiny red stars? We don't know, right? And that leads us to our next topic, which is the colors of the stars, right? So this application, then, we're going to make this available very soon, and we have all kinds of things. Like this is the Dumbbell Nebula that I mentioned before. And in the middle of the Dumbbell Nebula, you can see this beautiful white dwarf right in here.
Yes.
Yep. Yeah, 15 to 1800 light years away.
Amazing.
And it's actually glowing very brightly, and it's the size of the Earth. Right?
Wow.
Yeah, so that's how much what its temperature is. This bluish color is more like a green, actually. This bluish color is oxygen, and this red is neon and hydrogen that were released from the star's main envelope as the star began to pulsate as it got older. Then it shrunk down to a white dwarf, leaving this nebula around it. This is the fate of our sun right here. So there.
And we're seeing that straight on, right? I mean,
Well,
could there be a circle maybe?
That's a question. That's a question. Are we seeing it straight on, or are we looking at it at an angle? And thus, it looks like an apple core. Okay, you can see that
Yeah.
it looks like it's got this hourglass shape here.
You have that edge all around it too.
Yeah, see that?
Eyeballish.
And it goes even more. So here's the thing. First of all, and this is a good point to talk about. What we're looking at right there, okay, is called a bipolar nebula. No, it doesn't mean it has behavioral issues.
That we know about, yes.
That we know about.
Mm-hmm.
What it means is that the star's north and south pole is probably along this line that we're seeing right here, okay, that I'm dragging out. And this is the star's equator, and it was rotating like this, okay? And if it was rotating like this, okay, it means that as it was rotating like this, that material was being flung out along the equatorial regions like this, okay? And then you see these lines of red that seem to be like a shell. That seems to imply that as it was rotating, it was also doing this.
Wobbling.
And so if it was wobbling, as it wobbled, some of that hydrogen got flung down here, and it wobbled back, and some of that hydrogen got flung over here, and obviously symmetrically on the other side at the same time. Then there was some kind of event where a bunch of it got flung out right here. Not sure what that is. But you see, this is really strange. We're seeing this in 2 dimensions, but it's a 3-dimensional nebula. So we don't know what that looks like. Is it a sheet coming toward us? Is it a spindle going away from us? We don't know. See, but still, if you think about it, the Dumbbell Nebula, which is known as a planetary nebula, is a very fascinating object to study, right?
Mm-hmm.
Yeah. And the colors all mean something, as we said. But there you go. That is our application, and I think that's something that, like I said, we'll have it ready. I'm already in discussions with the company to get ready to license this and get it out there so that you'll get it. And every night, right now, it's updated nightly. So every time we actually, it's I should say streamly. every stream it's updated. So you can actually download an update probably after every stream.
Yeah, a lot of people do that already, or just go up and grab the photos.
Mm-hmm. That's right, and this makes it even easier because within here, like say we go here, and then go here, you can see right here. You can go
Can't
say,
see anything.
Oh yeah, you're right. Oh yeah, thank you for letting me know.
There we go.
Let's say you go into this object here, okay, and you click on it and say, "Ooh, what a pretty photo! Look at those blues! Look at those reds! I want to download that picture. What do I do? How do I get it?" Well, you click Ping File right here, and that takes you to our server. And instead of wading through directories, you can just say, "I'm going to download this picture." So what you do is you just say, "Download," right? And so we say, "Download the image," and it's right here. Download. Okay. And here it is. It's being downloaded in the browser. And then we open it. Okay. Now, what you're seeing is probably nothing because it's not the same window, I don't think. You probably won't see that. But this now opens as a very, very large image on your screen, full size.
Cool.
And that's bigger than your screen can handle. It's much, much bigger than your screen. So those are all free. We do full finished processing on all of these, and you can then take them down and use them. If you're a Patreon member, you get access to them at a certain level. So it's all stuff that you can do. Sorry to bring it back. I forgot to mention those things. Right.
Very cool.
Yeah, it's all cool. Yeah.
Thanks, Isabella. You're awesome.
Yeah. Oh, is she out there now?
I don't know, but she'll probably listen.
Oh, okay.
She's not.
Yeah. Yeah, no, it's true. So Carl Becker asked a question, which is kind of good. Does Isabella stack 2 images and stitch between 2 to see the differences? Or is there a program which analyzes the 2 images? I'm currently writing a program that will take the images, however many you have, and load them all in and just automatically check for differences between them. But the first thing it has to do is scale them all to the right scale. So luckily, they're all taken with a similar camera, same camera for the last, year. Before that, a different camera. So depending on whether it was taken with the older camera we had or the newer camera, we would change the scale appropriately. But that's one number; it's one constant value, and we get the new scale size. Then we have to align them to each other and then subtract them from each other. And whatever's in there is something that wasn't in one of those photos.
Cool.
Right?
You make it sound so easy.
Well, it's a difference analysis. But now you got to do that. You got to do that in a very interesting way. Let's say you have 3 images. You have to subtract image 1 and 2, image 1 and 3. Right? And now you're going to see a difference. If there's something different in 1, 2, or 3, you'll see the difference in that stack of images.
Mm-hmm.
Now you have to determine which image shows the difference. Okay. So now you just have to figure out which one has that image in it. And so now you go back and you compare each one to find that highlighted difference. That might be the thing you do once you get a flagged image saying, hey, this set of images you took shows difference here. Now, if you had 20 images, well, that's a little bit of a chore. We could write a program to chug through all that. But what fun is that?
Well,
what fun is that? You got to do it. You know. So we right now, I'm writing this program for Photoshop right now. And for those that think Photoshop is beyond their reach, it really isn't. Photoshop used to be a program you could like $500-600, $1,000, and they go, okay, I got Photoshop. Who can afford that?
Right.
Now what I do, for $10 a month, I subscribe to it. I have the latest version, and I can do anything I want. You know, I measure stellar distances. I measure stellar separations. I wrote little programs that they're called actions. I wrote actions that do all that. That stuff works great. You know, it's really, really cool.
Cool.
Yeah. So now, the next topic I want to talk about relates to some of the colors we've been seeing in these stars that we saw in the images I showed. And what do you think is hot? All right, Tara, what is hot to you?
Well, psychologically, I think red is hot. And, but I know it's a little bit different with astronomy.
That's right. It is.
It's so different. So.
Yeah, it is.
Mm-hmm.
Yeah, people see red hot and they think, oh, don't touch. And you're right, don't touch. But of the hot, red hot is the coolest of the hots. Yeah.
That doesn't seem right. But yeah. No. So it's the blue that's the hottest, right?
Right. And to figure that out, what you need to do is take a flame from like a torch.
Mm-hmm.
When you turn it on, you see an orange flame out here, and then there's a cone of blue near the middle. And there's a brighter cone of blue just before that cone of blue. The brightest cone of blue is the hottest point of that flame.
Mm-hmm.
We have a tiny little point. There's a second point of blue, which is a little cooler, right? And then there's going to be, from the blue, it's going to transition to a whitish yellow to orange to red.
Okay.
All right. Now, these are star colors. And these, in a star situation, as now you're getting, this color corresponds to the different temperature at the surface of the star. White dwarfs always look blue. When we take photographs of that dumbbell nebula I showed you, it had that blue cloud and the red. Well, the blue cloud and the red cloud of gas, that's a different process entirely. That's ionization of atoms. That's not related to the temperature of the star per se. Okay. What it's related to, though, when you look at a blue white dwarf, the white dwarf is that hot stellar remnant left behind by a star that has finished its existence. And it will sit there and be hot and cool off slowly. So it's a white dwarf. and it will eventually become a black dwarf. Now, in the history of the universe, there are no stars that have reached black dwarf stage. Not enough time has passed for a star like that to occur, right? In other words, a white dwarf hasn't cooled off to be this, dark cinder.
So that's a
over.
theoretical thing, a black dwarf?
It's theoretical, but is theorized to exist and will exist someday.
Okay.
Okay. Yeah. Now, the different types of stars are and have always been determined by the different colors, as we talked about. But there's several different factors that go into this, and let's put up this diagram here.
Oh,
Okay.
yeah. Okay.
Along the bottom, we see the bluest are the O stars: O, B, A, F, G, K, M. Now, O stars, hottest and bluest, and you can look up this top of that right there.
Mhm.
You go up there to that top right up there, and you see that these are like 60 solar mass stars, 30 solar mass stars, very, very, very big stars, right? Beta Centauri is one of them, and some of these are even bigger. Bellatrix in Orion, you can see right near the word main, just above the word main.
Oh, yeah.
Bellatrix. You see Betelgeuse, which is the upper right. In the upper right of this diagram, you see Betelgeuse up there. That's the red supergiant. That is the top left star in Orion. Bellatrix, on the other hand, is the one across from it in Orion. It's the next part of that square that makes up those 4 stars in Orion before the bell. Okay, so Bellatrix is that next one, and it's a blue, massive star. It's pretty big. I forget how many masses of the sun it is, but it's quite large. Spica just is on its way down, and that's 10 solar masses. Again, this is an O/B star. You can see that sort of straddles the border of the O and B's that you see there.
Yeah.
And the O stars are really hot. Their surface temperature is above 30,000 Kelvin. Now, 30,000 Kelvin, you can convert that to a Fahrenheit, and it's going to be extremely hot, right? So it's going to be somewhat higher than that in Fahrenheit, all right? Now, the reason we have a Kelvin scale is because we would like to be able to have an absolute scale. We don't want to have a negative temperature in astronomy because we use the temperatures as parameters in many equations, such as Wien's law and the luminosity law, Stefan Boltzmann law, all these different laws within astronomy. So we use Kelvin. The lowest temperature you can have is 0. That's absolute 0. That's minus 400 and change Fahrenheit. And then of course you can you can take Kelvin, and 0 degrees Kelvin is minus 273 degrees Celsius, right? And, yeah, I know, that's still cold. Yeah. And then so forth. So why so many temperature scales? Well, Celsius would be the ideal one to use, but we can have negative temperatures there. So Kelvin, if you're looking at mathematical equations, you don't want to have a negative number show up when you need positive numbers. So that's a simple reason why I like Kelvin. But the O stars up there at the top, the hottest and the bluest, 30,000 Kelvin. And, they're extremely hot. So Bellatrix in Orion is one of those types of stars. Alnitak in Orion, the leftmost star in the belt, is one of those types of stars. Another star called Zeta Puppis is a type of star like that. Okay, and so they're very hot. Now the caveat is that even though the stars are hot, they're still actually fusing hydrogen into helium. And that's what this squiggle line going down the middle. You can see this line kind of traveling down this thing here. Each of those stars all appear in like this line. Hang on. That line is called the main sequence. And the main sequence is all, quote, normal stars, stars that are fusing hydrogen to helium normally. That's what we're seeing here. Now, so that and it turns out that Ejnar Hertzsprung and Henry Norris Russell discovered that, in fact, the stars that are fusing normally all seem to appear on a line. And this became a definition for classification of stars. Ended up being something really impressive because we use it all the time. Now, moving on from those O stars, right, we go to B-type stars. And B-type stars are bluish white, and their temperatures are between 10,000 and 30,000 Kelvin. And they're still hot and they're very luminous. And they, just like the O stars, they give off lots of ultraviolet light. O stars, the brighter O stars that we see up there at the top, most of their light that's coming off is in the ultraviolet. Like, imagine a split second getting a tan, and a split second having a full body dark tan.
Wow.
That's what you get in a split second with one of those stars, if it doesn't fry you entirely. Famous examples of those are Rigel, the lower right end of Orion, the lower right corner of Orion, and Spica, Alpha Virgo, Alpha Virginis. Okay, so those are the B's. So the A stars are next, and those stars are typically white. All right, and the temperature of the A stars is on the order of 7,500 to 10,000 Kelvin. You can see how the temperature level is dropping. And these are less hot than O and B stars. And their spectra is very characteristic. They have these nice, strong lines of hydrogen that we can see in them. And to give you an example, right now, when the sun sets tonight, and you go out and you see Vega, the brightest star in the summer sky, that's one of these. It's an A star. And Vega is, we call Vega a standard star for us because it's 0.0. It's actually perfect. It's right there in that perfect spot.
The Vega Goldilocks zone.
Yes, exactly. And then Sirius is another example in the winter sky. Sirius is the brightest star in the northern hemisphere, and it's brightest because it's about 8 light years away.
Closer.
But it's an A-type star. Yes, exactly. It's closer. Yeah. And we move on and we get to the F stars. Now we're looking at like a yellowish white, 6,000 to 7,500 Kelvin. And slightly hotter than the sun, not by much. And they often have lots of other lines in their spectrum that we can identify. As an example, in the winter sky, we have Procyon. Okay. Remember, you have Sirius and then Procyon, the two of Orion's dogs. Right? Well, Procyon is the higher star in the sky. Sirius is the brighter one. And then we have Canopus, which is another star that's an example of that. Now, I don't think I have to tell you any examples of the next sky, the G stars, but the temperature is between 5,200 and 6,000 Kelvin, and that equates to about 10,000 degrees Fahrenheit. Okay, surface of our sun, 9,900 Fahrenheit, and they're medium stars, medium temperature stars. Now, as we move down this list here that we're seeing, every one of these stars, from the O stars down to the red way at the bottom, there's longer and longer lifespans associated with these stars. Okay, O stars may only last a few million years. Okay, B stars a little longer, A stars longer still, F stars longer, G stars typically about 10 billion years.
Wow.
So imagine lasting only a few million years or lasting upwards of 10 billion years. Well, that's what we get with our sun. Okay, it's about 10 billion years. Now, examples, of course, are the sun and Alpha Centauri. All right, Alpha Centauri is a G star. So moving on, the K stars, they are more typically orange, and they're between 3700 and 5200 Kelvin. You see the temperatures are dropping now, and they're cooler than the sun. They have sometimes in their outer atmospheres, they can actually have molecules, whereas in stars like the sun and less, they're so hot you can't have atoms making molecules. It's too hot, you know. But right now in the night sky, you can see Arcturus. Arcturus is a bright orangey star in the sky. It's sort of yellowish orange. And Arcturus is, in fact, a K star, right? And then we have Aldebaran, which is a little more red. Aldebaran, right near the Pleiades, is also a red star, all right? Now, finally, we get to the M stars. This is the coolest star ever out there in the universe. In fact, they're cool for a lot of reasons, not just in temperature. Give you an example. Proxima Centauri, the little red dwarf, they're called. And the temperature goes from 2400 to 3700 Kelvin. And when they have planets around them, the planets can be really, really close to the star. All right. And the planets, when they're really, really close to the star, are very much they're able to be in a habitable zone around these red dwarf stars. And that habitable zone is right up close to the star, you know.
And
So
you can live there?
yeah. The habitable zone is so close.
That's
An
weird.
example is TRAPPIST-1. Okay, TRAPPIST-1, a red dwarf. Okay, again on that snaky line we saw. All right, TRAPPIST-1 is a star that actually has a habitable zone that is so small that there's 7 planets around TRAPPIST-1 we've identified. 3 of them are in the habitable zone around that star.
Okay.
And all 7 are well within what would be the orbit of Mercury around our sun.
Oh my goodness.
So
and that's because it's so much cooler than the other sun.
That's right. It's so much cooler. So it's possible that M stars are these amazing little incubators for life in the universe. Why is that? Because these M stars are more populous than any other type of star. I call them the universe's percolators. And the reason is because no red star that's ever been in existence has ever yet died. They last trillions of years. Plenty of time for a star to go through a youthful phase where it's shooting off all kinds of ultraviolet radiation. Poof. Okay. And plenty of time for it to find its way back to being stable again. And it's not going anywhere anytime soon. See? So that's kind of cool.
So when we are looking for habitable planets that we could maybe travel to in the future, we're not bound by just the same type of sun that we have. We can, I mean, it really broadens our basically zones that we can go to, right? Or,
Absolutely correct.
Okay.
Yeah. We can start looking actually from A stars on down. O stars and B stars, too much ultraviolet. Ultraviolet light sterilizes things. Okay, look what it's done to Mars from our sun. Our sun's like a G star. Now, our Earth is safe because we have a big, thick atmosphere. And we have a magnetic field. And a lot of the dangerous radiation and dangerously charged particles are shunted away from us by the magnetic field and our atmosphere. So we're protected down below in this little sheath, this little cocoon.
Thank goodness.
And yeah, and that's why we survive. Right? Mars, on the other hand, Mars had an atmosphere like ours, but its magnetic field started to shut down. And over time, through potential impacts and the shutdown of the magnetosphere on Mars, Mars' atmosphere was eroded away by the ultraviolet light striking things like water molecules in the atmosphere, splitting the H2O into 2 hydrogens and an oxygen. The hydrogen gets lost to space. The oxygen dives down into the ground.
And turns red.
Bonds with iron compounds. That's
There you
right.
go.
And then what's that turn into with the iron?
Rust.
Rust indeed. And so
Mhm.
you see, this girl's smart.
I'm learning a lot. Yeah.
You are.
Cool.
Yeah. So, so that's really important to understand. So a red star, the coolest, most common star there is. Um, now a little wrinkle is that if we go back to our chart for a minute, you'll see that on the right side you see M. But if you look at the top of that chart, okay, if we look at the top of this chart way up here, okay, you can see that we also have like a star named Betelgeuse up there. Now wait a minute. Betelgeuse isn't this tiny little dwarf. No, the chart along the bottom is the color of the star, okay, and the temperature. Now, it doesn't have to do with the size of the star. The size is something related to another thing called luminosity, which is this vertical column here. Now, luminosity, if I showed you the equation, you'd see that it depends on the radius of the star, the second power of the radius, as a matter of fact. So the larger the radius, okay, the larger the luminosity. Okay, so high radius stars are going to have a high luminosity, and when a star goes into the phases of its life off this snaky line called the main sequence that you see going down the middle here, okay, then it starts doing a different process, and that process takes it into super gianthood, red gianthood up there, and when that happens, the star will end up going into its final years and evolve. But it's only the temperature, not the size, which determines where that star is on that scale. The other thing that determines where it is on that vertical scale is not the temperature, but the luminosity. So we have something called a spectral class, the color, and the luminosity class, the brightness based on the radius. So those two together make the spectral type of a star. So we have a two-pronged approach to defining how stars look. Right?
Interesting. So it doesn't matter the size or whatever, they all fit on that sequence.
They all
All
fit
of
in,
them
and
did.
they all fit in that diagram. Okay,
Mhm.
in one place or another. In fact, if you look at the bottom of the diagram underneath the main sequence, that's the realm of the white dwarfs.
Mhm.
Why is that? Well, because they can still be hot, okay, and have a variety of colors. If you notice, Sirius B is really quite hot. All right, it's literally less than 0.1 the sun's luminosity, right? All right, but that's because it's so small in diameter. But it's still like a star that's between O and B in hot temperature. So again, that's the size of the Earth, but it's so close to Sirius we can't actually see it without doing special processing, basically.
Wow.
Yeah. So these stars all have their place in that diagram, and there's every single kind of star will fit in there somewhere.
Mhm. So is it right that the blue stars are the ones that are going to blow up most likely, and the red stars slowly fade? Is that right?
The ones that are on the snaky line, yes.
Okay.
Okay. Now, by slowly fade, uh, um,
Let's just
slowly fading stars are stars that basically go through a process where they make a planetary nebula and then shrink slowly over time. So the way that works is this: stars burning hydrogen. Let's take our sun. Hydrogen burning into helium. Well, the hydrogen is going to run out someday. So that's going to mean the star is going to start to collapse a little bit because there's no more outer pressure pushing out, holding the star up. Because the hydrogen pressure, the energy pushing out is lessening. So the star begins to collapse. That heats up the core. And now what that does is by heating up the core, now the helium that's in there, the helium that was made in that core can get hot enough to fuse. And now the helium will start to fuse into and makes this new source of energy. And the star goes, aha, and it swells and it becomes a red giant with this newfound source. Okay. Then the helium begins to run out eventually, and the core begins to collapse again, and it gets hotter and hotter and hotter. And then finally, it may start burning into carbon and other things and shells around that core. Again, boom, it goes up again. is a red giant. And then after that, it shrinks down to a white dwarf when it finally runs out of all of its source. That's for a star like the sun. For a star like Betelgeuse, on the other hand, which is now already a red supergiant, what we're looking at is a star that was an O-type blue star. Betelgeuse started life as a bright blue hot star.
Okay.
In fact, 4.2 million years ago, when Lucy, our predecessor hominid that walked on two legs in Olduvai Gorge, looked up at Orion, Lucy saw 4 blue stars on the outside of Orion. Betelgeuse was bright and blue. Okay. And so it over the intervening millions of years, it used up all its hydrogen, swelled up into a red giant, and then started fusing helium into carbon, swelled up into another red giant. Now it's a supergiant. If you put Betelgeuse where the sun is, it would actually go almost to the orbit of Jupiter.
Wow.
That's the whole star inside that volume, a whole star. Yeah. So that said, we're talking about massive amounts of space and spherical, space that a star takes up, a volume. That's huge. And that volume of space by that star, okay, Betelgeuse now, having been so massive, Betelgeuse has a lot of mass in its core. All right. And so Betelgeuse is destined to go supernova. And we're eagerly waiting for that to happen. I hope it happens soon.
Yes.
Now, Betelgeuse is about 500 to 700 light years away. So it had to have happened. If it happens like 700 years ago, then we might see it in our lifetime because the light train is still coming to us.
Gosh.
Isn't that crazy?
It is crazy. That's that time machine.
That's right. That's right.
So, but now instead of being blue, it's real red, right?
That's correct. That's correct. Want to say hi to Eliza Raquel? Hi there. Thank you for joining us from California. Then we had this question from E-Man. Heard of a hypergiant? What is that? And are they bigger? Yes, they are. Hypergiants are relatively theoretical. I don't know that we've actually found a true hypergiant yet, but it's an exceedingly massive star that when it goes supernova, I imagine it'll be incredible because we'll see it in our daytime sky with no problem. When Betelgeuse goes supernova, we'll see it in our daytime sky, like a second star in the sky, just much fainter. It won't be as bright as the sun by any stretch, but it will be several times brighter than Venus, that's for sure. And it will look bigger in the sky to us.
And we can look at it.
And you can look right at it, yeah.
Yeah, that's cool.
Yep. I can't wait. I'm going to turn my telescope to it in the daytime, and take images of it with the daytime scope. And right now we're waiting for a star in the constellation Corona Borealis to go nova. Okay.
Oh.
And a nova is a different thing. Okay. There's so many ways stars die. We have these planetary nebulae and then a white dwarf. We have a supernova boom, which makes a neutron star, or a supernova boom, which makes a black hole. We also have this other process, and that is that if we have a star that is hang on a minute, I'm brain fart. I was going somewhere with this.
Different ways. No, never happens to me, Mark, ever.
Oh, good. I'm so happy. Yeah, no. I was trying to remember. I had several thoughts in my head. I'll think of it.
You will, and we're out of time, I think, as well.
Yeah, we're at 1954, 754 right now.
That's it.
Well, it'll have to wait till next week, but boy, it was a great idea. Anyway,
I'll remember it about 1:00 this morning.
No, I'll remember it as soon as we could disconnect. I want to thank everybody for joining us tonight. Thank you for all the folks I see all the time in our streams. Thank you, Tara. As usual, you're just tremendous. And we'll be back hopefully next week, back to our live shows. Good night, everybody, and thank you for coming.